Today's topic, the cross product of two vectors. So previous lesson we talked about the dot product, and now the cross product is another way to multiply vectors. Dot product resulted in two vectors multiplying and coming out to be a scalar. Today we're looking at two vectors being multiplied in such a way that they become a vector. So what is today's goal? I want you to be able to identify the cross product when it would be required, and in principle how it works, and I want you to be able to use the appropriate skills to determine the value. So that means that I need you to be able to do the cross product. I can't stress how important it is to be able to do dot product and cross product for Unit 2. Unit 1, it's just going to be, do the calculation for me. Unit 2, we're going to be applying it, so it's very, very important that you have that down and you're comfortable with it. So, an example here. Same as the work example. A wrench is tightening a nut, so I better put the nut in. So here is my nut. I'm just going to keep it simple. Just a square nut, a rectangular nut. Discuss the forces that are involved. So since you're not here, I'll discuss them myself. The nut is pivoting about this point. So what are the two factors that are involved in increasing how I can tighten or the torque itself? So how much force is applied? How much force is applied? And the length of lever arm. So any of the people who are watching this that have tightened anything before, worked in the shop, the longer your wrench, the more torque or tighter you can make an object. So I mean, the two factors are involved. In this case, is the length of the wrench, and if I put my hand on the end of the wrench and pull there, the force, the magnitude of the force, is also a factor. Now, that magnitude of force will vary, and I'm going to go back to the previous notation, so let's call this point A, this point B, so this is vector AB, and this is my force vector. And we're looking at how it's related there with torque. So it's just a force times length. So our torque is equal to our force, and now it's multiplied by our length. Now, the result, when you do a cross product, is a vector. Because what's actually happening here? Okay, at the source, okay, when you are turning or twisting something, we have either tightening or loosening occurring, which means that there's a force going in or out of board. So therefore, force into screen or out of screen. Okay. So when you're tightening something, it's pulling two plates together. So think of it as tightening, you're putting a bolt through two boards. When you tighten it, you're pulling the two boards together. So the forces A and B are parallel to the boards, but the force, the resulting force, is going perpendicular to A and B directly into the board here, into the boards, tightening them together or pushing them apart. So very, very important that we recognize that. Now, going back to number 1 here for a second, I'm just going to put here the angle in which it's applied. So some people here are going to be saying maximum force is when you're pushing at a 90 degree to your lever arm, and that's absolutely correct. When you are in this course, if you can't get the right leverage, the angle theta, which is measured on the exterior side here, plays a role. Okay, so the actual formula that we're going to be doing, a resulting formula here then, will be exactly this. So it's going to be torque is equal to magnitude of force. Well, first of all, it's going to be force cross AB, which is equal to magnitude of force multiplied by magnitude of your length multiplied by, and I'm looking at this angle here, in order to find that component. So let's say the force isn't perpendicular. Let's say it's applied at an angle. So let's say it's applied at this angle. We want the component that's pushing perpendicular. So we need to take that force vector and we need to take what's called the y component. So if you think of it in terms of our axes being placed here, here's your x component, or x-axis, y-axis. We want the y component. From earlier in this course, the y component would be sine theta. All right, and the formula that we're going to be using is just going to be vector u cross v. This is in general terms, or magnitude of u, magnitude of v, sine theta. Now, because there's a direction involved here, I'm going to take a step back. Up here, we have to insert what we call n unit vector n hat, and that indicates a direction. And we'll talk about that in more detail as we go on. A direction, therefore, you know that you're going to end up with a vector. All right, so this is probably the format or the formula that you're going to put on your cheat sheet for yourself right here. Okay, those are the two forms, and I'm going to talk about each one as we go here. So we have something called the right hand rule. So that means you need to use that right hand, and it's going to be a little tricky, so this may have to be explained when you see me in person. The right hand rule is applied because we can model three vectors, the force, the torque, and the lever length, using our fingers. All right, so applied force, and I want to get this right. This would be your applied force is your middle finger. And please don't be giving it to me at this time because I can sense it through the video. So middle finger, that means you, Warren and Jacob. So applied force, that's your middle finger. Your torque is going to be your thumb. And the lever length is your pointer finger. So if this is going to help. Pointer finger. And for the gearheads in here that have been in the shop, you'll know this rule as the righty-tighty, lefty-loosey rule. So in general, we point our fingers along vector u and curl our fingers in the direction v. So we're going to take our pointer finger and we point it down. So pointer finger's red. So right now, you want to point your finger with your fingernail at this end. This is the way you're going to point. And you are going to, in this case, we're going to do a clockwise rotation. So now you're going to put your, orient your hand so that your middle finger is pointing in this direction somehow. So you got your pointer finger pointing with the red arrow, and you have got twisted your middle finger to point with the blue arrow. Your thumb is now pointing into the screen here. So your thumb is centered there, pointing into screen. Into screen. And that's the direction of force. Okay? So we are tightening or loosening. So when it's into screen, you're tightening. Hence the rule righty-tighty. So you're twisting it right. Okay? A clockwise rotation. So you're getting a tightening. If we were to change the blue arrow direction, so let's say that we started twisting the other direction, change my direction of rotation. So now that means that your middle finger, you have to flip your hand over, pointer finger on the red, middle finger has to point in direction of blue arrow, the thumb is now pointing out at you, so then you'd be loosening. Okay? I'm going to switch this back to match up with the rest of the diagram, but that's the general rule. So this is the righty-tighty, lefty-loosey rule. We call it the right-hand rule in the math world. If you need help with that, I can clarify that when we meet in person. Notation. Okay, I've gone through this already. Your u, v are just your vectors, and the sine theta, I've identified it on the opening page. N indicates direction. Direction perpendicular to u and v. All right. So some general properties here. Okay, and these are important because they're a little bit different than dot product. Okay, the first one is it's not commutative. That means that dot product, 2 times 3, is equal to 3 times 2. With the cross product, it's not true. 2 times 3 is not equal to 3 times 2. The difference being, it is actually the negative of it. So we have u cross v, and in the brackets I switched it v cross u. To make them equal, they are the negative of each other. Okay? And that's to say that basically you're changing direction here. Righty-tighty would be tightening into the board. This one would be the lefty-loosey. It's coming out of the board. So to make them equal, I would have to make one negative so that they're in the same direction. For non-zero vectors, u and v, so that means that they have a magnitude other than 0. Both vectors are collinear. That means they're on the same line. Okay, collinear. There's vector 1. There's vector 2. If and only if u cross v is equal to 0. So if we do and that's a vector, 0 vector. If you do the cross product, and the cross product turns out to be the 0 vector, then you have collinear vectors. All right. It's not the most efficient test, and the previous stuff that we talked about was much more efficient for proving collinearity. 2 vectors are not collinear if u and cross v is not equal to the 0 vector. And that's absolutely a stunning revelation after seeing point 2, I realize. Okay, but stating the obvious, I guess. Number 4, for vectors u, v, and w. So if we have 3 vectors, and I'm doing the cross product of u cross v plus w, okay, it is equal to our distributive law. So u cross w, or sorry, u cross v plus u cross w. So our distributive law still works. In the reverse, u cross w plus v cross w, and remember order is important here. And finally, the scalar, again, doesn't matter, u cross kv. All right, so there are your properties. So they are different, okay, than the cross product or dot product. Number 1 especially is different. 2 and 3 are really the same. And then number 4, our algebra rules still apply. Okay, your general algebra rules that we talked about in grade 9 still are in effect here. So I'll leave it at this point, and we'll move on to the next video.